Okay, thank you very much for the invitation to talk here. And I'm sorry that we're not all together in Bonn, but this is the next best. So thank you so much. Yes, so I will be talking about some applications of sharp large deviation estimates and asymptotic convex geometry. This is joint work with mainly Yin-Ting Liao, who's maybe in the audience, and as well as another PhD student of mine, former Stephen Kim, who did more work on just the large deviations. So I'd like this to be interactive. So please do just interrupt at any time and ask questions. I don't have to get through everything. I'd rather just have more interaction. And I'm very much looking for questions that may lead to sort of more possible applications than the ones we've identified of these methods. Okay, thank you. So I'm going to start. Of course, we know that asymptotic convex geometry is trying to study high-dimensional objects, either convex bodies or in high-dimensional probability, high-dimensional measures. And often you take the dimension to infinity, or you can look at these high-dimensional objects and look at their low-dimensional projections, and then you take the dimension to infinity and see what these low-dimensional projections do. And we've seen that, high dimensions often imposes some sort of regularity, which has a probabilistic flavor. So classical results in asymptotic convex geometry have focused more on law of large numbers and central limit theorems. And now I'm talking about, sort of prior to the last, maybe 4 or 5 years. So just to give you a very, very incomplete and, small list, so there's some work of Schechtman, Zinn, Schechtman, Schmuckenschlager, etc., to study the volumes of intersections of LPO walls, about which I will talk more at the end. Then Barani and Wu talk about CLTs for Gaussian polytopes. Mech is looking at CLT problem for random vectors. Klartag and the CLT for convex sets, of course, building on previous work of Antilabal, Perisinaki, Brem, Voigt, and many others, going back to Sudakov and all. And then there's been Powers, Pivovarov, Zinn, looking at volumes of random projections of cubes against CLTs, and so on. So it's a very incomplete list, but there's a lot of work that has been done in looking at CLTs, and many that I've missed from here of Thaler and other people as well, also in the last 5 years. So this is sort of just going back a little more old. And so just as I highlighted here, the CLT for convex sets. So of course, we all know that if you have a high dimensional random vector, which is distributed uniformly on an isotropic convex body, and then, the projections. So if you take a random direction on the sphere and then you take the scalar product, that's what I mean by the projections, or the fluctuations of that projection, which is given by the Sexton theorem, are Gaussian. So that's, yeah. So of course, this was Antilabal and Perisinaki showed how, this was sort of a more precise statement. And Antilabal and Perisinaki showed that if Xn satisfies what we call a thin shell condition, then most projections are almost Gaussian, right? And then they verified it for certain classes of LP balls, and in certain classes of balls with certain Holder continuity conditions on the boundary, which included LP balls. And then Klartag actually showed that more general than balls, just isotropic log concave measures satisfies this thin shell condition. And then, further bounds have been derived by Mekes and other people. So what is this thin shell condition? So this thin shell condition is just a condition on the norm of the vector suitably normalized by root n being close to 1, typically in the isotropic setting, but I'm just writing it in a slightly more general form if you're not, normalizing it in the isotropic way. So then you're just saying that the norm, scaled norm, Euclidean norm of the random vector concentrates in a suitable way. So if you have that thin shell estimate, then you know that you have projections that are Gaussian. So of course, we know that the CLT is a universal result, and this result is very beautiful, but it does imply that looking at the fluctuations of lower dimensional projections does not provide sufficient information about the high dimensional objects, because most of them look Gaussian in most directions. And so, of course, there's been work in trying to identify these sort of singular directions in which it doesn't look Gaussian. But another approach is really, why not look at tail behavior? if maybe large deviation principles that would allow one to distinguish between different objects, right? So, you can have different tails here. And so it's more easy to see than just looking at fluctuations, which all look the same. So that's the idea, to look at large deviation principles and see if we have, which are typically non-universal versus the universal CLT, and to see what we can say about them. So just to recap, I'm sorry if this is a repetition for people who know, of course, large deviations very well, but just to recap that this is a sequence of random variables is said to satisfy a large deviation principle if, roughly speaking, the probability that Wn lies in A decays exponentially, and with the exponential at some speed Sn, and then some exponent Ia, which is typically given as the infimum over some function, which is called the rate function. So this is a good thing to keep in mind, knowing that this twiddle, which is an approximation, should be thought of in the sense of these log equivalents. Okay. Okay. So, of course, a very classical result of large deviations is saying that if you look at Cramer's theorem, so if you look at the log moment generating function, and if it is finite in the neighborhood of 0, then the normalized sum, or the average empirical mean, satisfies an LDP with the speed and the rate function, which is given by the Legendre-Fenchel transform of this log moment generating function. So that's a very classical result that goes back to 1938. But a geometric point of view is to really say that this empirical mean is nothing but the scalar projection of this xn being the n-dimensional vector with the ith component xi along the 1, 1, 1 direction, suitably normalized to be on the unit cube. Okay, but we are interested in, potentially not just projecting along the 1, 1, 1 direction, but project along random directions, right? So you might ask, okay, let's look at not just IID random vectors. We might want to look at sort of more general random vectors. And so a natural thing to look at as a first case in convex geometry is to look at LP balls, for instance. So if you take xn now, coming from LP balls, and you make this 1, 1, 1 direction more general and theta n being random, then you have this sort of, I'll write xnp's uniformly on the scales LP BPN, which is the unit ball in LP. And this cap theta n is a uniformly chosen from the L2 ball, or the L2 sphere, right? And then you define the projection as simply being the scalar product, but now I've scaled it by an additional 1 over root n, because I'm looking at large deviation principles. So I want to look at how Wn fluctuates at a order of root n, so that the scalar product at root n. So I divide this by 1 over root n, as you would do for just the 1, 1, 1 case. So here, just going back here, if you want to do 1 over n, then you would have to take 1 over root n times the scalar inner product of these two things. Okay. So now you look at these projections, and there are two sources of randomness, as I've said. So one is coming from this random direction that I'm choosing uniformly at random from the sphere, L2 sphere. And there's the annealed, where I consider both randomness at the same time, both xn, which is chosen uniformly from the LP ball, and then the theta. So we would want to understand the behavior of these WNPs and ask whether they satisfy large deviation principles. So we started looking at this with Nina Gantert and my student Stephen Kim a while back. And yes, it turns out that the answer is yes, that you do have a quenched large deviations, as some of you may have seen this result before, that for almost every direction on the sphere, the sequence W theta NP satisfies an LDP, which means it decays exponentially with speed n. So it's like e to the minus n something. So the probability W theta NP is greater than A is like e to the minus n. And then times this I, this exponent is IPQU, the quenched, QU being quenched, evaluated at A. Okay, so you do, the answer is yes, you do have this. And, but the interesting thing is, what am I doing? I'm choosing, what is theta? theta is actually a sequence of directions that I'm taking, where the nth component is taken from the n-1 dimensional sphere in Rn, right? And then I'm taking, let's just, for simplicity in this talk, let's say that I'm choosing it IID across dimensions. And then you choose a sequence, and then I'm saying that W theta NP satisfies an LDP at speed n. A priori, this W theta NP, the rate function could depend on theta, right? Depend on the sequence of directions that I chose. But it turns out that it doesn't. And that's why I do not have any theta mentioned here. It's just, it's irrespective of what sequence of directions you chose, you're fixing them. Remember, it's quenched. So you're conditioning on that sequence and then looking at the random variables and seeing how they decay. But irrespective of how you choose that, you always have the same rate function. And that's not true when p equals 1, but it's true otherwise. Okay. So, but the rate function is typically different from Cramer's rate function, right? So we're saying that I can choose any sequence. So you might choose, okay, let me choose this 1-1-1 sequence that I'm very familiar with, and which I'm familiar with in the product case. But even if you choose it for the LP ball case, if you choose the 1-1-1 sequence, an LDP still exists, but that rate function is different from this universal rate function in some sense, which universal in terms of theta, or insensitive to the directions. Okay, so just going back to this quenched random approach, I'm conditioning on the random sequence, and then we have this result. To give you some additional remarks, remember the whole idea was in the CLT, we said that if we looked at just fluctuations, you don't get any information about the higher dimensional object. And here I'm saying LDPs, in contrast to CLTs, do carry some geometric information. Why? Because this rate function, which I haven't written explicitly for you, but it has a pretty explicit expression, this depends on P. So it varies with P. So it's not like the Gaussian case where you take any LP and you look at the fluctuations, they look Gaussian. You don't know which LP ball it's coming from, isotropic LP ball. Whereas here, if you look at the tails of the projections, you should be able to, at least if you know the rate function, then you can say which P it is, okay, which LP ball it's coming from. Any questions so far? Okay.
Yes, maybe. So once again, almost every means with respect to the product measure on n-1 dimensional spheres.
Yes. So actually, the only thing I need, I can be more general about, I can choose any measure on the sequences such that their marginals at the nth dimension is uniform on the sphere. Okay. So I do not need IID, but that's a good just example to keep in mind. Mm-hmm. But all I need for this to hold is just that the marginals are uniform on the sphere. And one can, even if you want to choose something else other than uniform, under a certain condition, you can also get a quench rate function, but I won't go there for now. Okay, but if somebody wants to ask me about that, I can tell you. But for now, we're just doing uniform on the sphere since that's the most natural. Okay. So we've been told that, so we see that, maybe this is a fruitful line of inquiry because the LDPs, in contrast to LDs, seem to carry geometric information. Okay, but unfortunately, however, these rate functions, they're good, but the rate function, so I could have chosen my xn, I chose it from the ball, I could have chosen it just from the sphere, right? Which would not be a convex body, but it's still an object, and it's a random variable, and it's a measure that I'm projecting down. And the rate function would be the same. So it exists and everything, and it would be the same. So it does not distinguish between, so the large deviations rate function, the tails, do not distinguish between balls and spheres. So while it's nice that it gives you some geometric information, it captures the LP. I mean, this is, of course, a consequence of the fact that a lot of the mass is on the boundary, right, of the sphere. So what's inside is not, but the thing is, you have to be careful when you say large deviations, because when you see a lot of the mass on a CLT level, that's quite different from saying a lot of the mass on a large deviation level, because you really need a lot of the mass on the boundary. And, quantifying that, you have to be careful. So this doesn't distinguish between that. And so if you would like something that maybe is more refined and could potentially tell the difference, maybe you would be more greedy and try to do some more calculations or find some other estimates that would give you information like that. So with that in mind, we wanted to see if maybe because remember the large deviation principle only gives you sort of this log asymptotics, right? It only tells you sort of that the decay rate is I, and it tells you the speed. But it really doesn't tell you what's in front of that exponential e to the minus ni, right? So, which we will call, let's say, sometimes it's called the prefactor. So the question is, can you get more information somehow on this prefactor and provide more geometric information? Firstly, can you even get that? Because it's not obvious that you can for general bodies. And if so, is it useful? So just to remind you that when I say this twiddle, it really means this. So I don't really know what's in front of here. All I know is if there's a Cn over here, then I know it's of order less than, 1 over Sn. So I just don't only know the order of that Cn, right? That log Cn over Sn goes to 0, but I don't know anything more than that. Okay. Okay, so why would I expect something like this to be true? So if we go back, the CLT for convex sets was like, okay, a lot of high dimensional measures seem to be behaving like IID random variables. And we have this sharp large deviation principle for IID, for sums of IID. So let me explain this a little slowly. So if you have an IID sequence of non-lattice random variables, so they can't be regularly spaced, and again, you go back, you have this log moment generating function, and I look at the empirical mean again, and I want to look at it, see how it deviates greater than or equal to A. Then, of course, I have this e to the minus nia, which I knew from the large deviation setting, but now I have a correction. And now it's only up to a little O1. It's still asymptotic, but it's only up to a little O1. So in some sense, large deviations is useful. It's giving geometric information, but it's asymptotic theory as n goes to infinity. This gives you sort of more in the spirit of the local theory of one-X spaces, tells you something, so a little O of 1 for a fixed n, it's giving you more refined estimates. And so here, what you can also say what exactly these constants are, where sigma A is given in terms of this, derivatives of the log moment generating function at a certain point, which can be explicitly identified, but I'm not telling you exactly what it is here. Okay, so this goes back, as I said, to the 1960s again, and so I was sort of curious, can we extend this? Is there a similar? So the thing is, like I said, why would one be interested in this again? So you might be, there are many reasons, because not only are the refined results, might give us more information for high dimensional statistics and asymptotic convex geometry, but also it could be useful for those who know what important sampling is. If you want to calculate probabilities, very small probabilities, so volumes of very, very small thin shells, which are very small in large N, then actually knowing this prefactor can be useful in developing efficient techniques in which to sample. Okay, so as I said, we have a product measure, and we have this classical result of Bahadur-Ranga Rao. And then you might look at the quenched random projection of the product measure. Right now, I'm only looking at product measure, the simple case. And all I'm doing is I am saying that now, instead of looking in the 1, 1, 1 direction, I look at a random direction, right? Chosen uniformly from the sphere. That's what my theta I is. And then I condition on this theta I. Then what I get here is a weighted sum of independent random variables, but not identical. Right, so I cannot apply Bahadur-Rao as it is, because these are non-identical. So, because of the theta I weights, because I fixed the theta I. If you were allowing the theta i's to be random, then it would not be a problem, because then theta i's are sort of equally, distributed. There's some dependence, but it's very weak. So the question is yes. The answer is yes. It turns out that you can calculate, you can prove a Bahadur-Ranga Rao result for this, and it looks very similar. So I change, this is even for, not only for product measures, but even for LP balls. I have this rate function as before, which is the rate function which goes with the LP ball naturally, but then I have this correction, which has the same form. It has like root 2 pi n, and then it has my gamma coquant. The question is that true? Okay, so I'm not saying this is how it is. I'm asking, do we have something similar? No, and it looks similar. Do we have something like this? So that's what we're trying to investigate. Okay. So it turns out that you do when it's a product measure, and we want to see what happens for LP balls. So why am I talking about so much about LP balls? Because it goes back to representations by Schechtman and Zinn and also Rachev and Ruschendorf in the 90s, that early 90s, so that you can write this BPN, which is the uniform measure on the ball, as so let's say on the sphere, you can write it as being the normalized. So you take a vector which has this density, which is just proportional to e to the minus the absolute value of x to the p over p. Just like in the Gaussian case, if you wanted to you have a representation for the sphere, right? Like you could take, you have this you can represent the uniform measure on the sphere in terms of Gaussian random variables by taking the Gaussian random vector and then normalizing it by its L2 norm. So here we're saying we can do something. We can take IID random variables from another distribution, which is just x to the p over p, proportional to e to the minus that's density, and then normalize it by the LP norm, and you get a uniform measure on the sphere. And then if you want the ball, you have to take another uniform 0, 1 random variable and then multiply that in front. And this is just a normalization constant to scale the ball appropriately. Okay, so this is probably well known to many of you, but this representation is very useful because somehow you're looking at this sort of dependent structure, but it's sort of represented in terms of IID random variables, and that's why it facilitates many calculations. Okay, so when we have this, we show that for any p strictly between 1 and infinity and strictly positive a, where IP of a is finite, so that the rate function, there's actually a decay, then the probability indeed has this structure. So we now do refined. So this e to the minus n IPA over here, that is the rate. That's the only thing that you know from the large deviations. Everything else here is a correction. Okay, and what is the correction here? So there is a correction here which looks very much like we thought we might get, right, from the IID case, which is this root 2 pi n and this gamma p star, which is different from the gamma p that you get in the product measure. But what is interesting here is now you get a factor which depends on the particular direction in which you are projecting. And you get a correction factor in the exponential, which is of order root n, which you do not get in the product case, but you do get in the LP case. Okay. And so this shows that this refined LDP has already got two advantages over the large deviation principle, which is one is that it is telling you something about the geometry also in terms of dependence on theta n, because you know that the LP ball is not spherically invariant, right? So there is obviously some effect there, and it's capturing more geometry than that. And it's also, so it's not insensitive to the theta n direction, right? So just like and I have not written this here, but it also can distinguish through that between balls and spheres. So that's two things that it can do. And I'm not going into the details of what this, this constant is, but it's pretty explicit. And HPA is a particular matrix, and CPANs are constants, which we have written in our paper explicitly. So you can look at them. I will tell you a little bit more about these constants. But are there any questions at this point? I want to point out here that this CPAN theta n and this RPAN theta n, they're random variables, remember, because they're coming from this theta. I mean, they're functions of theta n, which is chosen from a distribution. But over here, you're fixing the theta, and then they're functions of the theta, right? But you can also view them as jointly some random variables, and you might want to understand what they look like. And it turns out that so like I said here, this constants gamma p, it looks similar in both cases, but the constants is different for balls and spheres.
Sorry, okay. I do have a question.
Yes, please.
But can you say something then about the growth of R and C?
I'm going to just thank you for I'm going to just tell you about that.
Okay.
Yeah. So I'll tell you that in the next slide. So so it turns out that we will come back to this, but in the quenched projection, you do not have the same structure as you do for the product, the IID, the Bahadur-Ranga Rao, you have this additional terms. And now coming to Nicola's question, so on the constants, I want to tell you about these CPA, theta n's, and square root of, like I said, this part is coming from the large deviations, and all these things are extra. And what can I say about these two constants? So these two constants together, they converge weakly to a precise functional, which we have written down, of a centered Gaussian vector. So you can actually understand how this fluctuates in terms of theta as well. So that's the information we have about this. Does that answer your question?
Yes, I think it does. I need to think about it, but thank you for the
Okay, thanks. And so the way we do this is sort of you have to look at this. We write this, of course, as a function of the theta i's. And for any f theta I, we know that the theta I ends themselves look Gaussian, right? But you have this f, which is a nonlinear function. And so you have to expand it in a suitable way and then show that this joint functional converges weakly to the functional of a centered Gaussian vector. Just to give you some idea of the proof, it's you know that the individual theta i's are, of course, looking Gaussians. But you have to look at the whole vector, and you also have to look at a nonlinear functional of each of the coordinates. So it's, but you use some sort of Taylor exponential and some structure in order to prove this. Okay, so coming back to sort of what is the additional geometric information, can we just look at the constants and say something else? Maybe this is also useful, Nicola, for your question. So if I look, I mean, of course, this CPA is important, but this is obviously the more dominant term, right? Because there's a square root of n decay that it is inducing in the large deviation rate function. And so if you look at the maximum of RPAN over the sphere, you might get some idea of where do you have the maximum decay, at least at the exponential scale, even if it's not e to the n, but e to the square root of n, and where do you have the least decay? And we know, so that's an interesting thing, that this additional geometric information that it gives you is that the maximum of this over the sphere is attained at the, over the plus minus 1 directions when p is greater than 2, and it's the coordinate directions, in the p. So it's like the 1, 1, 1 type directions when p is greater than 2, and the coordinate directions p is less than 2. And of course, many of you know, things about the geometry of LP already. And so in this case, you might say, yes, I know that I have more mass on the 1, 1, 1 direction for an, L3 ball, right? And it's going to be over here when it's an L1 ball, right? So this can be, of course, this we know about LP balls, we can do it in different ways, but the point here is to show that the sharp large deviation estimate, if I didn't know more about LP ball, would tell me that about the ball. So maybe it's worth actually getting these sharp large deviation estimates quenched in other contexts where maybe you don't know, and you can use this in order to understand how the mass is distributed. Okay, just a sketch of the proof. As I mentioned, you can use this Pth generalized Gaussian random variable, which when Riemann normalized gives you the distribution on the LP sphere. And you can write that, writing it in terms of that, you can write this S bar NP just being this sum belonging to some domain, where this domain, if you rewrite it in terms of this, is just some three-dimensional domain. So I'm rewriting my probability in terms of these, without the details, but then rewriting this probability in terms of certain IID sums, where here my S bar NP here is given in terms of these generalized Gaussian random variables and their P norm. So this is the P norm to the P, okay? So I'm taking the P norm, and then of course I have to worry about my, where I am on the ball. So if I'm looking at just the sphere, I only need these two. If I'm looking also at the ball, I need this third direction, to tell me where I am on the ball. So the point is that this nice IID representation allows you to write this probability in terms of a three-dimensional vector lying in some domain, and then you have to get sharp large deviation estimates for that. Now, you still cannot apply a Bahadur-Rao kind of thing, firstly, because it's multidimensional, and then you have to worry about the structure of the domain, and then you also have to worry about the fact that these are not IID, but they're at least independent, but not identical, right? So there are all these extra things that you have to do. But you can see that it satisfies an LDP with that rate function that we have a particular rate function, but then we have to obtain an asymptotic estimate for the density as well, and not just the rate function e to the minus n. So you need to get some prefactor on the density for non-identical, and the way you do it is by doing a certain transform, which is sort of what is called tilting in large deviation, and looking at sort of quenched CLTs for those non-identical random variables. So I won't have time to go into a lot of details on that, but that's the basic idea. The basic idea is you find the large deviation principle. Once you find the large deviation principle, it tells you a certain measure that you can do, which you can transform the measure under which the event that you're looking at becomes sort of likely, or with probability 1 asymptotically. Then under that tilted measure, you want to look at a CLT and get a quantitative CLT for that. And that's sort of the general spirit, but you have to get an asymptotic estimate like that, and then use a Laplace type approximation and properties of the domain in order to be able to compute this. So I hope I've given you a flavor, even though obviously I don't want to write all the formulas over here. Okay, so like I said, the key takeaway is to get, like I said, the sharp large deviation estimate. You have to identify a certain change of measure under which this rare event that you're looking at becomes typical, and then establish quantitative quenched CLTs under this change of measure. So now what you can do is, given this, I just want to show, a particular, you can use this change of measure that you identify and to compute just in a particular case, because I mean, you might say, okay, how good was this refined estimate? Do I really need it? Do I not? I have a lot of plots in our paper, but this is probably not the most stunning plot, but I just want to tell you how well it tracks the oscillation. So what is this plot? This is dimension. Okay, x-axis is dimension, and the y-axis is the tail probability, and you can see that it's in 10 to the minus 70, 10 to the minus 60. So that so it's very, very small, right? And we're trying to compute what is this tail probability. Obviously, it's becoming smaller as dimension goes large. And so normally you can't compute that, right? If you just do Monte Carlo simulations to compute this, you will be, because you're looking at 10 to the minus 60, you simply can't do that. But you can do what is called important sampling algorithms using this change of measure to compute this. And so what I have here is what this blue line here is what the large deviation principal rate tells me that the probability is, okay? And the red line is, which is, they're all on top of each other, so you can't really see that it's a red line, but the red line is what the sharp large deviation estimates tells me. Okay, this is for some fixed theta that I've chosen sequence. And it tracks the important sampling very well, the I. And in this particular case, we looked at a particular case in the L infinity when you actually know the exact one. You can compute the exact probability, and you can see how well it tracks. So you can see that the large deviation would give you a very sort of rough estimate. And here, this will actually give you a precise estimate. Now, because we were just doing the product measure, it's not that obvious that you're getting so much of a gain. You might be, oh, I'm quite happy with this line. I don't really need these fluctuations. But if you go to LP balls, then you actually just get a different slope, which you can see because you get this root n correction. Okay, so you can look at our paper for more. So it really does make a difference if you want to get some estimate. So analytically too, but it was just good to see computationally. Okay, so we have generalized this to multidimensional projections. and the quenched, where now you're quenching onto a random subspace and then, so you take a random two-dimensional subspace and then you project it, and then you look at the large deviations, and we've got sharp estimates for that in the quenched case. And I think a special case of our thing or a similar thing has been covered in recent work last month by Tom Kaufman, who looked at sharp asymptotics for Q norms of random vectors in high dimensional LP balls. We looked at the multidimensional projections and their norms. So what he did was look at one-dimensional, but not only projections, but also just you take a one-dimensional, you take a sample from the LP ball and look at its norm and look at sharp large deviations for that. So, so his work was sort of not in the quenched setting. I think it's in the annealed setting, which I will come to now. So the questions that remain is, okay, fine, LP balls are great. They're very amenable to calculations. Can we go beyond that to non-product measures? We know that the thin shell condition tells you that the random projection is close to Gaussian. Do we have another condition that will tell us that a random projection sequence will satisfy an LDP? So that's one question. And then you would like that in the case of multidimensional subspaces, where you're projecting onto a dimension of a subspace, which may be even growing with n. As we know in the CLT, a work of Meckes has shown that, of course, and Klartag and lots of people have shown that if you take a fixed dimension, you still have a multidimensional Gaussian, but you can even allow Kn to grow up to a sort of log n over log n factor, which is sharp, 2 with a 2 sharp factor shown by Meckes, when you will still have a Gaussian projection. And then if the n goes larger, then you don't. So it's interesting to look at multidimensional subspaces where the subspace may also grow with n. And then the sharp, which is what I want to say, some people may have seen the large deviations results here, but the question is, can you get sharp large deviations in that setting? Okay. So for this, I am going to I talked to you about quenched, and I want to give you some idea about annealed, because that will lead even more to a question in asymptotic convex geometry that is even more maybe central than looking at sort of probabilities of tails of projections. So let me just remind you that you look at the thin shell condition, which was of this, which is saying that the Euclidean norm of the vector suitably normalized concentrates. And you can think of M as 1 if it's isotropic. And what we developed was, it's a particular case of our theorem that we developed with Kim and Yin-Ting Liao, that the sequence of scaled norms, so the same thing here, where here I have been explicit about it being a 2 norm, if it satisfies a large deviation principle at speed n with some rate function, and if the rate function has a unique minimum, then you can show that it will also satisfy a thin shell estimate. Okay, so we're going to choose, we said that if we have a thin shell condition, we have CLT or Gaussian projections, Gaussian marginals. So the theorem that we have, so there are several examples of things that satisfy this asymptotic thin shell condition, but the main theorem is that if this asymptotic thin shell condition holds with some rate function Jx, then the projections also satisfy an LDP at a certain speed, which can be given explicitly here in terms of the original rate function of the scaled norms. Okay, any questions on that? So the next question we had, and this is just for one-dimensional projections here that I've written, but we've done this for multidimensional projections and norms of multidimensional projections, etc. But the thing that I want to emphasize here is really to ask, can we get refinements? And I will tell you why. I'm not just saying, oh, whenever I have a large deviation, can I get a sharp large deviation? I'm going to tell you why I would want to do it. There's an estimate. Okay, so what is this estimate? So now we have a general condition which is called the sharp density condition, which in particular wants the asymptotic thin shell condition to hold in the following way, that you want this scale norm to satisfy an LDP with some rate function. And here I've just written it a little differently. I've written it in terms of the random variable squared. It's just more convenient for what we want. So just here it was the, here it was the norm divided by root n. I'm just taking the square. Okay, so it's really the same. The square will satisfy an LDP if and only if the original one does. So this is essentially the asymptotic thin shell condition A star that I put last time. And then if I define this dj to be the domain of the rate function, and now I suppose that the assumption is that this also has some density, Fn, that admits a certain asymptotic estimate of this form. So we know, of course, from this that the point 1, that you expect Fnx to be looking like something to the e to the minus nj of x. That you know, but that you know only up to log asymptotics. But here I want to know a little bit more about the prefactors. So if I know this for some alpha and this, and I want this to hold uniformly in a compact neighborhood, any compact neighborhood of the domain, then what we say is that you can get a sharp large deviation estimate. Okay. And so what you get here is this, of course, some constant. And here now you have n to the alpha minus 1, where you can think typically alpha is half in many of the examples, but this is more general. We can consider other cases. So this would be like a 1 over root n gamma an, right? Which was of the form of the 1 over root 2 pi n of the Bahadur-Ranga Rao. Any questions on this? So remember what I'm doing is, what I'm saying is that if I have a sequence of random vectors, xn, so which you think of as maybe uniformly on some ball or some other high dimensional measure, sequence of measures, if they satisfy the sharp density estimate, then their projections will satisfy a sharp large deviation estimate. Okay, that's the result. And it's given all explicitly. I'm not writing down all the rate functions here. And remember, over here, you have the product measure. So now I have to tell you examples that satisfy this, right? So of course, you give some abstract there. You have to have some examples. And I'd like to go beyond LP balls, right? That was my goal. And so I'm just talking about one-dimensional projections here, but we can do this for norms as well of higher dimensional projections, including those that are growing. Okay. So just to remind you, let's look at Orlicz balls. So V is an Orlicz function if it's convex and satisfies, it's symmetric, and V0 is equal to 0. And I am going to sort of have a sort of a sharp, a sort of more stringent definition of superquadratic, which I want V to be differentiable and V prime x over x go to infinity as x goes to infinity. Okay, so we think we probably can relax this a bit, but right now that's what we have. So if you define this Orlicz ball in this way, right, in the particular case when V of x is x to the p with p greater than 2, this will clearly be satisfied, right? And that's the LP ball, right? Okay. That's what and of a certain radius, it would be of radius n to the 1 over p. Okay, so now I'm defining this Orlicz ball like this. And then we can define a certain function j in a suitable way. And then we showed in our paper from last year that if you have this uniformly, then in fact, this norm does satisfy an LDP with another rate function given in terms of this function. Okay, so this is just saying that the assumption A star holds, which was condition 1 of the STC. Okay, and the proof of it really, you were looking at things of this form because you wanted to look at the L2 norm of this. So you had to look at sort of 1 over n, the L2 norm of uniformly distributed from the Orlicz ball. And you can write that in terms of ratios of certain volumes. Okay. And so in the process, we really got some, we had to actually find, to prove this, we had to find some results. We had to get results on the intersection of the Orlicz ball with the 2 sphere of a certain radius. Okay, so the point is that in the process of proving this, we had to prove something about intersections of Orlicz balls with L2 balls in some sense. So that led us to saying, okay, but that was just first, that's just a comment. And by a corollary of this, of course, because we said that the asymptotic thin shell condition holds, we also have that the projections satisfy some LDP. Okay, but that's one. But then we wanted to prove the sharp density condition. And so this, it's not really important exactly what the conditions are, but I just wanted to say they're explicit. I've given you this h of x. It's given in terms of the determinant of a Hessian of that function that I put, j of x, and then you take square roots and do certain things, you take some derivatives. So there's an explicit expression for this h that we wanted, and alpha is equal to half. And so it turns out that, yeah, for Orlicz balls, we can prove that the sharp density condition holds. Okay. And so what is the corollary? That if you look at projections, then you get the sharp estimate. So you not only get a large deviation, but you also get a sharp estimate for the projections. And we can do this for multidimensional projections and Orlicz norms of Orlicz balls and things like that. So we will have that paper out. But I'm just giving you one example of just one-dimensional projections where you can get the sharp large deviation estimate. Any questions? Okay, so you might say, okay, fine. I mean, you get a lot of estimates for projections and that's nice, maybe. But maybe look at something that's maybe more central. Of course, volumetric quantities are very important in asymptotic convex geometry. And as I mentioned, that it's part of the proof, we had to look at intersections of different kinds of Orlicz balls. So very recently, in a very nice paper, Kabluchko and Prochnow have looked at some sharp volume estimates of Orlicz balls. And they also looked at this volume ratio of, take a Orlicz ball of radius R1 intersected with another Orlicz ball with another radius R2, and then look at the ratios. Okay, I'll tell you more about there. But before I do that, I wanted to explain, you go back to the particular case of LP balls, this kind of question of the understanding how intersections behave goes back to Schechtman and Schmuckenschlager, and Schechtman and Zinn, and then Schmuckenschlager. So what they did is they showed that if you normalize this, the BP ball so that it has unit volume, and that's this hat represents normalized for unit volume, and you look at the intersection of one with a certain multiple of the other, then you get this phase transition such that there's some explicit constant CPQ, that its t is less than that, it goes to 0, and if t is greater, then it goes to 1. Okay, now remember that when q is larger than p, then BQN, right, is going to be contained in BPN. So that's why you sort of blow it up to see what's happening. Okay, so this is a very interesting result. And of course, this begs the question, what is happening at t is equal to CPQ, right? I mean, because you have this phase transition, what's happening at the level? And that was answered a decade later by Schmuckenschlager, who showed that it goes to half. But maybe two lines about how this is proved. And that will sort of relate how you get, why the study of norms. So, we were studying random projections, and we saw that to study random projections, you needed to understand sort of the Euclidean norms of these vectors. And it turns out that in a similar, and then that led to sort of study of volumes. So here you have that same thing, except in the reverse direction. You want to study volumes, but you can write that as the ratio you take using that particular representation that I told you in terms of generalized P random variables for LP balls. You can write this intersection as the probability. You take a random vector in the LP ball, you look at the ratio of its Q norm to its P norm, and you look at the probability of it lying in some domain, okay, or being less than something. And that the volume is governed by an integral which has that term in it. Okay, but now when you have IID random variables and you're looking at the Q norm and the P norm, you know that they're going to concentrate. They're going, as n goes to infinity, they're going almost surely to some constant. So if you're looking at the probability that it's greater than or less than something else, it's either going to 0, it's either going to 1. Right? So essentially what they did is they looked at a weak law of large numbers for a randomly chosen in an LP ball. Okay. And so, of course, if I was on the blackboard, I would have written these details out, but I didn't want to put it all in the slide. But it's essentially just a weak law of large numbers that they used. And that was not good enough to show what happens at the boundary, because you don't know the rate at which it's sort of going to this constant, and so you can't really control that. So Schmuckenschlager looked at more refined estimates, but again, you're using this fact that you have these IID random variables and looking at the LQ norms and LP norms of them, of their sums to the P. And he looked at sort of CLT fluctuations, suitably normalized, again, wrote this probability down in terms of the sort of normalized random variables, wrote it in terms of Gaussians, and concluded that it goes to half, okay, at the critical value. So that's back in 2001. So then 2 decades later, going beyond the LP case, so Kablichko and Prochnow, again, in that nice paper, said, okay, let's look at the case when you have Orlicz balls. And as Yin-Ting Liao and I had also some estimates on this that came out from the particular case when one of them is an L2 ball. But here, and we were not looking at this problem, we were just looking at the asymptotics of the volume because we needed it for proving something about the norms. But here they beautifully showed that there's again a phase transition. So you have this 0, 1 feature over here, where again, if your certain constant CR1 is greater than R2, then it's 0. If it's less than R2, then it's 1. Okay, so the ratios of these four. So of course, the question is then what happens in the critical case? And what they used is they actually used a large deviation estimate, because now remember, when you have Orlicz balls, you don't have this representation. So while the result looks similar to what was done by Sheckman and Schmuckenschlager, the approach is really quite different. Okay, because you cannot use that representation and you cannot directly use those results. So you actually have to use sort of a tilting of a measure and then look at its typical behavior. So I don't have much time to get into that, but just to give you a flavor. But that's not enough to understand what's happening at the critical case. And so it turns out, so this is just to, what we show is that we can get sharp large deviation estimates for the intersection. And they don't really look at the intersection and get sharp large deviation estimates, but they look at the ratio directly, right, Yosha? And so, but here we look at the intersection and we can get sharp large deviation estimates for that using the theory that we developed. Or sort of it comes along the way. So it's not an application, but it's really a consequence of the proof. And then we show that at the critical case, in fact, this ratio converges to 1. So in fact, the point is that the original result holds even in the Orlicz case under, of course, the condition. We have a condition, and I haven't, maybe I'm sorry if I've not written it. We do have a condition on V2 and V1 and how they compare, which one has to sort of dominate. So V1 prime over V2 prime is going to infinity. So the other case is actually also interesting, but something else is likely to happen. Okay, so I just wanted to say that these sharp large deviation estimates, and besides giving sort of a good handle of probabilities, actually can be used to compute volumes and phase transitions and tell you what's happening at criticality and things like that. So it might be a useful method in other contexts. So just to summarize what we know about annealed random projections, we know that the thin shell condition implies a CLT, an asymptotic thin shell condition implies annealed LDPs for projections, and sharp density condition implies sharp annealed large deviation estimates, which then, or the proof of those things can also be used to get volume estimates for various Orlicz balls and things like that. And I will not have time to go into that, but we have also results in the sharp least deviation for what happens when you look at norms of random vectors chosen from Orlicz balls, which are projected onto multidimensional, possibly growing subspaces, and see how it changes. So, I'm sorry, that's it. Sorry, just repeated this. I went back, I think. Okay, here, yeah. So that's my summary. That with both the annealed and the random, the quenched. In the quenched case, we saw that you have sharp quenched estimates, and that can give you sort of more geometric information about directional importance, which you don't get from annealed because you're averaging over the directions. Whereas the quenched ones tend to be harder also because of the lack of symmetry, but they're also of interest. And these are just some references of our work and others. Thank you.